In this work, I describe our experiences over 6 years of developing a usable battery range testing and diagnostic tool for the mobile industry. My name is Abhilash Jindal, and this work was done with Charlie. So to begin with, I want to first describe the status quo of battery range testing and diagnosis in the mobile industry. During our 6 years, we learned that there are some apps, such as small apps with small teams, that did not have any battery range testing. These apps were just busy shipping features. Then even for large apps, the ones which have daily app usage of less than 5 minutes, we learned that they also did not have battery drain testing. But apart from these exceptions, we learned that the other players had battery drain related setups. So in the next setup, the app developers have black box testing, but no diagnosis. So for instance, a music player app would play music for 10 hours and they will consider that the test has failed if it drained too much battery. But this is not ideal, as the app developers told us, because this would sometimes delay the app release, as now the developers have to figure out why the battery was drained. The third type of setup that we learned of had no battery drain testing, but some post-release diagnosis. So these developers would release their apps in the wild and measure the battery drain statistics. If the battery drain has become higher, they would revert their changes and try to push a new release. These developers told us that this was also not ideal because this would earn them bad reviews from the users. So we thought, can we build a better battery drain testing and diagnosis tool, especially because we have the fine grained energy profiler eProf built in our lab. To remind us, eProf is an energy profiler that has two phases, power modeling and power estimation. During power modeling, we run a set of micro benchmarks on a test device. And while running these micro benchmarks, we log some power events such as CPU frequency change. And we also measure instantaneous power by connecting to phone to a power monitor. Then these power events and instantaneous power is correlated to build a power model, which typically is a finite state machine. Here the states are the different power states consuming different amount of current, and the transitions are power events such as CPU frequency changes. Now, once we have this power model, we can start doing power estimations. In power estimation phase, the user runs some real apps and the profiler running on the phone logs the same set of power events that were being logged during power modeling. Then the power model and log and these power events are combined to estimate the instantaneous power. Moreover, profilers typically also log some app activities and combine the instantaneous power with app activities along with the energy accounting policy to estimate apps instantaneous power. So using these concepts, we had built eProf in our lab. eProf is packaged as an IDE plugin that runs on the laptop. A user interested in profiling energy would select the app under test on laptop and click a button called Start Profiling. The laptop is connected to a test device with a modified kernel. On the test device, they'll play with the app under test. Then when they are done, they can click Stop Profiling on the laptop and look at the energy results. eProf breaks down energy into methods and threads of this app under test. Next, we demoed eProf to different players in mobile industry, and we learned of 8 major requirements from mobile industry under 3 categories. Let's look at these requirements in more detail. So the first set of requirements were related to the setup of the tool. The first requirement was about automated testing. The industry told us that actually human hours are very precious in industry, and because eProf required manual testing, it did not work for them. They really wanted to run tests on unmodified devices. OEMs were concerned that some kernel processes actually do not run on rooted devices, and other app developers were concerned that routing nulls device warranty. So ideally, they would like to run these battery tests without modifying the devices. Further, OEMs stressed that they did not want any a priori power modeling because they were interested in testing the battery range of devices that were not even released to the market. The next set of requirements were around usability. Under usability, we learned that app developers really wanted to do short test runs. For instance, a music streaming app wanted to test a single user flow so that if the test failed, they can just send this user flow to the team responsible for the user flow and let them fix it. The developers also wanted to do long test runs, such as watching an entire movie, because some of the battery drain behavior are only exhibited during long test runs. And finally, they also wanted actionable insights. This is important because again, human hours are very precious in the industry. And by just looking at the report from the tool, it should be obvious as much as possible on how to fix the problem. This eases developer burden and saves them time. The next set of requirements were around fidelity. The battery drain testing and diagnosis tool should be accurate because otherwise the tool will end up confusing the developers. It should provide battery drain spike alerts, and these alerts should have very high fidelity. If the alerts had false negatives, then actually we will miss battery drain issues and they will creep into releases. And if they have false positives, then developers will start ignoring the alerts over time, rendering the whole setup useless. So in total, there were these 8 requirements. To address these 8 requirements, we completely revamped the design of eProf to build eTester. eTester can handle 7 out of 8 requirements. We do not handle no a priori power modeling. In this talk, I'll only discuss 4 requirements highlighted in bold. If you're interested about the other requirements, please read our paper. Let's look at some drastic changes we made to eTester for supporting automated testing. eTester workflow starts from the developer. Developer already has some tests written in their favorite testing tool like UI Automator, Espresso, or Robotium. We ask them to wrap the interaction that they want to measure the battery of using the API calls of test library that we provide. Next, when the developer pushes new code or pushes new tests, they will run through continuous integration. This continuous integration will run these tests on a test device. On the test device, we ask them to install a tester app. This app will collect the logs from the phone at runtime and send them back to the continuous integration setup. The CI setup is installed with the plugin. This plugin will upload these logs collected on the phone to the server. This server will turn these logs into energy numbers, and these numbers can be visualized on the dashboard by developers. Next, I describe the number of usability improvements that we made for creating actionable insights. To remind you, eProf did battery drain breakdown by Java methods and threads of a single app. But we learned this was not very useful for other mobile software, such as code written in C or in React Native. This also missed a lot of important interactions, such as with system processes. And these system processes are the ones that actually drain energy in complex apps. And it's hard to do method-wise energy accounting for other hardware peripherals like screen, GPU, and hardware decoder. So instead, we made a philosophical shift in eTester, and instead we just focus on system events. So eTester correlates power consumption to system events such as system logs, frames drawn on the screen, network sockets, and threads. So next, I show you a demo of eTester running on Netflix app sitting in the background. This Netflix app had a bug where it is consuming a lot of CPU power, even though it is just idle sitting in the background.
The timeline view of the test output shows the instantaneous power draw of individual phone components, including CPU, GPU, hardware decoder, screen, SD card, GPS, and network over the testing period. Further, it shows a recorded screen video, which can be replayed in sync with the power timeline, which is useful for showing apps running in the foreground. Since Netflix was run in the background, the video only shows the Eagle tester on the foreground. Since Eagle tester performs whole system energy profiling, the initial power timelines shows the power draw of all processes running on the phone. To examine the power timeline of all components of a specific process, The developer can select that process from a drop-down menu. Coming back to examining the CPU energy drain of Netflix, we select the Netflix process from the drop-down menu. The power timeline now breaks down the power draw into the individual threads of the Netflix process. Examining the CPU power, we clearly see that the Netflix thread process manager continuously drains a constant CPU power of 300 milliamps.
Okay, next I described the fidelity improvements we made to eTester. To improve the accuracy of eTester, we built accurate OLED and hardware decoder power models which were not present in eProf. To improve fidelity of alerts, we created novel testing methodology for obtaining highly repeatable measurements and a statistics-based battery drain spike alerting algorithm. To validate the fidelity, we did the following experiments. We ran six tests over popular apps on Nexus 6 phone connected to Wi-Fi. To report accuracy, we compare the total estimated energy from eTester with the built-in current sensor measurements. And to report repeatability, we measure coefficient of variation, which is defined as standard deviation over mean across 5 test runs for each test. We learned that the end-to-end error of eTester is actually always less than 5%. Further, we learned that coefficient of variation was always less than 5.5% for eTester. We see that coefficient of variation is typically higher when the test runs are short. When coefficient of variation is less than 10%, the setup is generally considered highly repeatable. So this shows that eTester achieves high fidelity. eTester was also used to study popular apps. Developers learned that Netflix version 6.4.0 consumes 300 milliampere compared to just 2 milliamperes of a previous version while it is sitting idle in background. Like we saw in the demo video, the culprit was this process manager thread, which turns out it was stuck in infinite loop on a wait for system call. And Netflix was able to fix this bug from this report in a later version of their app. eTester was also used to compare Xfinity Stream with CNN. Developers learned that CNN drains 27% higher battery when watching identical TV content. And it turns out this was because CNN was logging 4 times more logs in Logcat because they had accidentally left debug flag on in the released app. During these 6 years of transitioning an academic prototype eProf to a tool usable by the industry eTester, we learned very valuable lessons. We learned that actually the ease of setup and use is very crucial in the industry. 6 of our 8 requirements were related to setup and use, and this is often overlooked in research prototypes, but is very important in industry. We learned that different personas can have different requirements. For instance, developers cared a lot about actionable insights, QA engineers cared a lot about automation, and product managers wanted to do competitive analysis of apps. It's important for an industry tool to cater to all of these different requirements. We learned the hard lesson of academic perfectionism versus industry pragmatism. In industry, it's often important to quickly ship features even though they are imperfect. And I personally had a hard time getting my head around this. It's also very important to identify serious users. If you engage with non-serious users, then they will anyways not use the tool and it can hurt the morale of the entire team. So to conclude, in this work, we did a deep survey of mobile software vendors to uncover 8 requirements for a usable battery drain testing and diagnostic tool. We completely revamped the design of eProf to build eTester that fulfills 7 out of 8 requirements. We still require a priori power modeling. During this 6-year journey, we learned some very important lessons. eTester is now open source. Thanks for your attention.